Very good morning to all of my dear students. I, Gurpreet Singh, working as assistant professor at the Department of Pharmaceutical Chemistry at ISF College of Pharmacy, here to demonstrate you another practical of pharmaceutical inorganic chemistry. And this experiment is for PharmD first year students. And this is our second experiment in the series of online practical demonstration. The aim for today's practical is to determine the content of acetic acid in the given sample of vinegar. This practical has been taken from Vogel textbook of Quantitative Chemical Analysis, 5th edition, published by Longman Scientific, and page number is 324 to 325. So, experiment for carrying out a successful experiment, we required some apparatuses and chemical. Considering the apparatuses, we require volumetric flask, burette, conical flask, measuring cylinder, beaker, funnel, glass rod, burette stand, and wash bottle. In chemicals, we require vinegar, which is our sample, and we are excluding the apple cider vinegar or the other natural vinegars which have been obtained from fruits because they contain some color which might interfere with the final results. So we are using a non-fruit vinegar that is a 8 to 10% solutions of acetic acid in water that are available in market at a very low cost. So we are using that sample to exclude any other color interference. Sodium hydroxide, it is used as titrant. Oxalic acid, it is used as primary standard, which must be used to standardize the prepared sodium hydroxide solution first. Phenolphthalein, it is used as indicator. Distilled water for the preparation of solution and for washing of apparatus and other glasswares. So let's start with the introduction. In the introduction, first we learn volumetric analysis is a general term used for a method in chemical quantitative analysis in which the amount of substance is determined by the measurement of volume that a substance occupies. It is commonly used to determine the unknown concentration of a reactant. Volumetric analysis is often referred to as a titration. That is a laboratory technique in which a substance of known concentration and volume is used to react with another substance of unknown concentration. We have some terms which are widely used in these kind of analysis. These require volumetric analysis. It involves the preparation, storage, and measurement of volume of chemicals for the analysis. Next is volumetric titrometry. It is a quantitative chemical analysis which determines volume of solution of accurately known concentration required to react with the analyte whose concentration you are going to determine. Or in other words, the volume of titrant required just to completely react with the analyte or the titer, or the process is known as titration. Titration, a process in which a standard reagent is added to a solution of analyte until the reaction between the two is just completed or judged complete. Primary standard, a reagent of solution whose primary standard, a reagent solution of accurately known concentration is called primary standard. Primary standard हम उसको बोलते हैं जिसकी concentration हम अच्छे से जानते हैं, which is highly pure, which can be easily measured, which is easily available, which is always cheap. Standardization, a process to determine the concentration of solution of a known concentration by titrating with the primary standard is the process of standardization. Endpoint. The endpoint in a volumetric analysis. Volumetric analysis is the signal that tells the analyst to stop the addition of reagent and make the final reading on the burette. It is generally observed with the help of indicator. Indicators are the auxiliary compounds or the solutions of the auxiliary compounds which show color change in acidic and basic conditions. there may be the examples for indicator are acid-base indicator like phenolphthalein, redox indicator, KMNO4, and complexometric indicator like iriochrome black tea or solochrome black tea, and there are other more indicators. They work on the principle that they can be able to show the color change in the different conditions. Equivalence point, the point at which the equivalent or stoichiometric amount of titrant is added to the analyte based on the stoichiometric equation. Or in other words, we can say the equivalence point is the point where the amount of titrant and titrate are equal in the reaction. There is 100% completion of the reaction. Upon adding an extra drop, the indicator react with the titrate and show you the end point or show you the color change in the reaction, or it may be precipitation, it may be complexometric color change, or it may be acid-base color change. Neutralization curve. The curve obtained by plotting the pH as ordinate against the percentage of acid neutralized or the ml of alkali added on the Abscess curve is known as the neutralization, or generally known as titration curve. So I'm showing you a simple reaction of HCl and NaOH, that is giving you NaCl and water. There are 4 types of neutralization curve or neutralization reactions, like strong acid versus strong base, like the titration of HCl and NaOH, and strong acid versus weak base, the titration of hydrochloric acid against ammonia. Weak acid versus strong base, like the titration of acetic acid versus sodium hydroxide, and weak acid versus weak base, the titration of acetic acid with ammonia. In acid-base titration, the titration curve represents the strength of corresponding acid and base. For a strong acid and a strong base, the curve will be relatively smooth and very steep near the equivalence point. Because of this, a small change in the titrant volume near the equivalence point result in a large pH change, and many indicators would be appropriate to judge the endpoint. For example, litmus, phenolphthalein, bromothiamine blue, they can be used for the identification of the endpoint or end of the reaction. This is a normal titration curve of oxalic acid versus NaOH. Here we are presenting a change in the pH as we added the volume of NaOH to the titration flask. Okay. So you can see initially there is only acid, so the pH is quite acidic, and as you add more or more base, there is a slight change in the pH, and nearly it become steady, or it becomes 7. The solution is neutralized at 30 ml. And after that, it remains steady, it will steeply rising. And after that, when all the base has been, the acid has been replaced with the base, it start increase in the basic form. This is a normal titration curve. Assay. An assay is an investigative or analytical procedure in the laboratory, medicine, mining, pharmacology, environmental biology, molecular biology, for the quantitatively assessing or quantitatively measuring the presence, amount, or the functional activity of the target entity, that is the analyte. The analyte can be a drug, biochemical substance, chemical element, or a compound, or a cell in the organism, or the organic sample. The measure entity is often called analyte, and the measure or the target of the assay. An assay usually aims to measure an analyte's intensive property or express it in the relevant measurement units such as molarity, density, functional activity in enzyme, or in enzyme. For example, for enzyme, it is expressed in international units. Degree of effect in comparison of standard. Assay has become a routine part of modern medical, environmental, pharmaceutical, and forensic technologies. Or you can see in the second wave of corona, we are assessing the amount, we are judging the amount of the virus or the viral load in the human body to judge whether you are positive or whether you are infected by the coronavirus or not. This is also an example of assay. Other businesses may also employ them as industrial herbicides and field levels. Assays are in highly commercial demand and have been well investigated in research and development sector of professional industries. So next is the procedure for our assay. First, we need to prepare one normal NaOH solution. We know the molecular weight of sodium hydroxide is 40 grams. So prepare one normal solution by using this formula M by V into 1 by equivalent weight. Equivalent weight is nothing but the molecular weight divided by the acidity or basicity. Acidity or basicity is the number of hydrogen or OH can be donated by respective acid or base. So NaOH, it has only one OH group, it can be donated. So equivalent weight is also 40 grams. So if you prepare one normal, that solution is also represent to the one molar solution. So in the case of NaOH or monobasic acids and base, the normality and molarity are the same. So preparation of one normal NaOH solution, we have to weigh 40 grams of sodium hydroxide on a watch glass and transfer it to a small beaker and dissolve it into a water, and then you have to transfer that solution through the funnel into the volumetric flask of 1 ml. And then you have to add more of the water to make it to 1 liter. And then you mix the solution properly or by thoroughly shaking and pour the resultant solution into your stock bottle that can be closed with the rubber stopper. Preparation of one normal oxalic acid solution. The molecular weight for oxalic acid is 126 and it has acidity. It has 2 donatable hydrogens. So the acidity for this is 2. So the equivalent weight is 63. But we are preparing the one normal solution. So in that case, or one molar solution, in that case, we have to take the molecular weight consideration. So according to the consideration, we have to dissolve 126 gram of oxalic acid in a watch glass. We have to dissolve 126 gram of oxalic acid into 1 liter of water, and then we can place this in stoppered bottle. Then before going for actual experimentation or actual assay, we have to first standardize the sodium hydroxide solution. For that, what you need to do, first fill the burette with the oxalic acid solution up to 50 ml. As I have already told you, oxalic acid is a very pure acid and it can be used as a primary standard. Then pipette out 10 ml of sodium hydroxide solution into a titration flask. Add 1 drop of phenolphthalein indicator to the sodium hydroxide solution and mix it further. And titrate the solution against the oxalic acid solution until the pink color of solution disappears. As I have already told you, phenolphthalein is a very good indicator in acid-base condition. Phenolphthalein can produce pink color or dark pink coloration in basic condition, while it is colorless in acidic conditions. So as we add this into sodium hydroxide solution, it turns pink, and when you titrate it against oxalic acid, it will the pink color will disappear. And you have to take 3 readings with you have to take 3 concurrent readings from the burette with an error of plus minus 0.1 ml. Next is the assay procedure. For carrying out the assay, weigh about 20 gram of vinegar and make up 100 ml in graduated flask. Take 25 ml of this solution and dilute with equal volume of water and add few drops of phenolphthalein as indicated. And titrate this solution against standardized 1 normal sodium hydroxide solution. As a result of the dilution, its natural color will be reduced, so there is no interference with the color change of the indicator. After your titration is over, calculate the acid content of vinegar and express the results in gram of acetic acid per 100 gram of vinegar. You can use this factor. 1 ml of 1 normal NaOH is equal to 0.6 0.005 gram of acetic acid. Now we move towards to the demonstration part. Welcome to the practical demonstration of experiment number 2. For this we require NaOH solution, oxalic acid solution, vinegar solution, phenolphthalein as indicator, 2 measuring cylinder, titration flask, pipette, funnel and burette. First of all, clean the burette with distilled water. First of all, clean the burette with the distilled water. Then rinse it with standard solution. Rinse once more. And allow it to flow. Now mount the burette onto the stand and adjust it according to your own eye level. Now place a funnel at the top, close the tap and fill the burette with the standard solution. So our burette is filled up to 50 ml mark. Pipette out 10 ml of NaOH solution as I have pipetted out in this and add it to the titration flask. Add one drop of phenolphthalein indicator. As you have seen, I have already told that phenolphthalein is pink in basic conditions. Now we are going to perform the standardization of NaOH solution. So adjust the burette accordingly so that your flask should be easily placed. Start the burette so that 1 drop per second will be fall into the solution. Continue, swill the flask. As you can see, now the solution has been decolorized, so it marked the end point. Stop the burette and note down the reading from the burette readings. Take 3 readings for the standardization purpose. As our solution is standardized, now we are filling the burette after emptying and cleansing with the NaOH solution. With the standardized NaOH solution.
Now our burette is filled. Take 25 ml of the vinegar solution in a clean aluminum flask. Add 25 ml of distilled water to it. Add few drops of phenolphthalein indicator. Mix it well. Now adjust the burette accordingly and start the assay by adding it dropwise. As you can see, a minute color has been developing, but this color must sustain for 20 seconds. That will mark the end point of our titration. You can see a small color is developing in the titration when a drop falls, but this color must stay for 20 seconds. That will mark the end point of our titration. So as you can see, a bright pink color has been developed in our reaction. So this marks the end point of our titration. So note the reading from the burette, and it is 28 ml of NaOH has been consumed in this reaction.
In the second part of the video, we have performed the experiment according to the procedure. Now let's look at the observations. So these are the observations which are obtained during the standardization of sodium hydroxide solution. At the start of the titration, we have put NaOH solution into the titration flask, and we have added phenolphthalein as indicator, and the solution was pink in color. And after the titration, solution turns colorless. That was the end. And we have taken 3 concurrent readings. This is the reading table. We have taken 10 ml of NaOH for each titration, and we have found out the volume of oxalic acid consumed during the titration. So the average volume was consumed 9.8 ml. So by using the formula N1V1 N2V2, we have concluded that the normality of prepared solution is 0.98 normal, and that is equivalent to 1 normal. Next, we have performed the assay of the vinegar according to the procedure, and these observations have been made. At the start of the assay, the reaction mixture looks like colorless, as we have acetic acid in this, and acetic in the acidic condition, phenolphthalein is colorless. And at the end of the titration or assay, it turns dark pink, and this coloration marks the end point of our titration. And accordingly, we have obtained the reading, that is 30 ml of standardized NaOH was consumed to titrate the 25 ml taken amount of the vinegar solution. So amount, by using the factor 1 ml of 1 normal NaOH is equal to 0.06005 gram of acetic acid. So 30 ml will equal to 1.8 gram. And that means 25 ml of vinegar contain 1.8 gram of acetic acid, and 100 ml of vinegar contain 18 gram of acetic acid. And we have 1 liter of that solution, and by multiplying the factor, we came to know about that it contains 180 gram of acetic acid. These are the questions for Viva voice. We will discuss this in the practical demonstration. Thanks for your patience. Thanks for your patience listening and time. If you have any question, you can ask.